Okay, good morning, boys. I hope you both had a lovely weekend. As I said last week, I'm going to set you work on a Monday, a Tuesday, a Thursday, and a Friday. So this video's explaining what work I need you to do today. I want you in your Aldehydes and Ketones booklet to complete pages 9 and 11, and hopefully the contents of this video will help you do that. So we're going to start by recapping what we did last week, or what you covered last week, and it's nucleophilic addition. And we said that carbonyl groups were susceptible to attack by a nucleophile. So you remember from the video last week we had this definition of what a nucleophile was, which we learnt in AS level. So a nucleophile is an ion or a molecule with a lone pair of electrons that attacks regions of low electron density. And last week we looked at the reducing agent lithial and how it forms that nucleophile, that hydride ion, and how it works to reduce the aldehyde to form a primary alcohol and reduce the ketone to form a secondary alcohol. So hopefully you've got that in your booklet all completed. If you haven't submitted that in Google Classroom, I need you to send that to me, please, so that I can check your work. So at the top of page 9, we're going to start by just filling in the general reaction, or the general mechanism for when a nucleophile attacks a carbonyl group. And we're just going to represent the nucleophile as Nu for nucleophile with a lone pair of electrons and the negative charge. So it's the same process that we did last week when you were doing about the reduction with lithial. So do you remember, because there's carbonyl group present, the oxygen is more electronegative, so it's delta positive, and the oxygen is delta negative because it's more electronegative, and the carbon is delta positive because it's less electronegative than the oxygen. So the lone pair of electrons from nucleophile are going to attack that carbon delta positive. Okay, and then this double bond, one of the electrons from that double bond is going to go towards the oxygen, and we'll get our intermediate formed. So do you remember doing the intermediate last week, where we had the carbon, we have the oxygen with 2 electrons, the nucleophile is joined on here, we've got the R, and remember we said that the R could represent any carbon chain. For a ketone, both of them will be carbon chains. For an aldehyde, one of them will be a carbon chain. And then we also said that there's hydrogen ions present in these reactions. It could be because of the nucleophile, where it comes from, it forms a hydrogen. We'll see that later on in a wee second. And also from the lithial, there was a hydrogen ion present there. So the second stage of this mechanism is that the lone pair of electrons from the oxygen attacks the hydrogen, and we get this the hydroxyl group formed. So we're going to have the R joined to the carbon, the OH nucleophile, and the R1. And we'll talk about how we name the products forming depending on what the nucleophile is. Then it might have a different name to the compound. So if you want to pause the video and just copy that general reaction into the top of page 9, you can write down that this is a reactive intermediate if you want to. Okay, so you want to pause the video and fill it in top of page 9. So if it's lithial, we get alcohols formed, don't we? We looked at that last week. But if we have a different nucleophile, so if we move down further into page 9, it talks about if we have a cyanide ion as a nucleophile. So the cyanide ion comes from the hydrogen cyanide. So this is going to split into an H plus and a Cn minus. Okay, and the Cn minus, the cyanide ion, makes a really good nucleophile because it's got the lone pair of electrons on the carbon, and then it's joined to the very electronegative nitrogen, so it acts as a really good nucleophile. So the same mechanism is going to happen. This is the reaction just in the middle of page 9. We're asked you to do it. What happens when the cyanide ion attacks the ethanol? Okay, so we've got our delta positive carbon and the ethanol, our delta negative oxygen. Draw our curly arrows in from the cyanide to the carbon, to the double bond to the oxygen. Our intermediate then is going to be your cyanide there. If we draw all the bonds, we've got a triple bond between the carbon and the nitrogen. And then we've got our oxygen with a lone pair. And then the H plus ion from the hydrogen cyanide joins in. And our final product then, we get the OH group joined and the cyanide group joined. Now what we've got here then is we've got a nitrile, and last year remember we talked about the priority of these side chains. So the nitrile group gets the priority, and this hydroxyl group becomes a subsidiary group of the second group. So this is called like Or start with this carbon, 1, 2, 3. So it's propane nitrile. Not sure we've really learned about naming the nitriles before. And then we always give the cyanide group, or the carbon with the nitrogen on it, or the cyanide group, the priority or number 1. So it's 1, 2, 3, and it's 2-hydroxy propane nitrile. Now, the other thing to notice in this reaction is that we started here with ethanol with 2 carbons, and we ended up with 2-hydroxypropane nitrile. So the benefit of using a cyanide ion as a nucleophile is that actually the carbon chain increases by 1 atom. So we end up changing the carbon chain, and this is really useful for organic chemistry when they're trying to synthesize new compounds or they're trying to change the carbon chain in it. So further down page 9, it talks about what happens if it's a ketone and we get the cyanide on it. So there's 2 different things to look at. If the ketone is symmetrical, then or if the ketone is asymmetrical. So if the ketone is symmetrical and we add on the cyanide ion, so this is just an example. If we have propanone, this is the product that we'll get, and you can do the mechanism out yourself and check that I'm correct. If it's symmetrical, the product is not optically active. So you can see there it's not a chiral carbon because it's got 2 groups that are the same joined to it. However, if we have an asymmetrical carbon or asymmetrical ketone, so we have butane 2-one, then we will have an optically active compound or product that's formed, because we will have, if I just write down the names, I'll give you the names of these, okay? So for this one, it's 2-hydroxy 2-methyl propane nitrile. And for this one, it's 2-hydroxy 2-methyl butane nitrile. Okay, so again, the carbon chain increased by 1. But you'll see here, this is optically active because for this carbon, it is a chiral carbon where it's 4 different groups or atoms joined to it. So we can have the optical isomer of that one. Remember, we learned about this in our previous topic, what optical isomerism means. So we will get a racemic mixture formed of 2-hydroxy 2-methyl butane nitrile, where you have 50-50 of each of these enantiomers. If you're not sure what I'm talking about, you can go back and revisit that topic and check you know what a racemic mixture is and what an enantiomer is. Okay, or you can just rewind the video a wee bit and check you're happy with that. So I want you just to pause the video or stop the video. That's the end of the video. So if you want to just stop the video or rewind it, and you can rewatch that and check that you've got page 9 all filled in with those mechanisms, and then that you complete the questions on page 10 and 11 today, please. That's great, boys. Any questions or any problems, send me a wee message in Google Classroom or send me an email or in Teams. Whatever way you want to contact me, I'll reply. Thank you.